Good afternoon, everyone. Thank you for coming to our presentation of our autonomous traffic system. So here's just a quick outline of what we're going to be covering today. And my name is David. I'm the team leader, and I work primarily in the software team, but I also switch in between software and hardware when needed.
My name is Thomas. I'm the chief hardware architect, and I'm a computer engineer.
My name is Joe Ramos, and I'm a computer engineer, and I'm going to be the chief software.
So for project motivation, we wanted to create a system that would basically take into account autonomous vehicles, because nowadays autonomous vehicles are on the rise and they're starting to appear more on the road. So we wanted to create a navigational system that took into account the routing of autonomous vehicles as well as all the other cars within the system. So the societal impact of our project would eventually be if all of the cars were on our kind of network, it would lead to faster routing, safer driving, and basically just an overall improved efficiency between routing of vehicles, and both manually and autonomously driven.
So here we have our overall system architecture. We decided to show that through a functional decomposition. So here we have our level 0 with initial inputs of radio frequency tags and road conditions, which go into our autonomous traffic system and output an optimal route for each of the cars in the system.
So just a better way to describe our system is we went into more details with our level 1 of our functional decomposition. And we start on the left with the same inputs with the road conditions and the RF tag. These are both fed into our image recognition of our self-driving car. This is done through a RFID reader, a ultrasonic sensor, and a Raspberry Pi camera. This is all mounted onto a Raspberry Pi, which is on our RC car. This then sends the car sensor data and the obstacle detection data to our database, which stores the information in our route controller. The image recognition of the car also sends the location data to our local positioning system. When designing our small scale system, we knew we couldn't use GPS because it was too inaccurate for our small scale. So we created our own local positioning system by putting RFID tags all along our small scale model, and every time it drove over it, it would get a location. So then it takes that location data, calculates it, and changes it into coordinates, and sends that to our database. Our database then sends the data for our traffic and our car locations to our route calculation algorithm, which then calculates all the routes of each of the individual cars, taking into account minimizing the interactions between these vehicles. And then this is all sent to our route controller, which is an Arduino controlling each of the RC controllers that will send the signals to all of the cars individually.
So for our related theories, I wanted to cover exactly how we managed to create object detection classifiers. We were using the OpenCV library for Python. Through this, we were able to train our system into being able to detect clones. As you can see, like we used the hard-like features option to extract the wavelets within the images of our cones and build a classifier out of that. And then after that, we had to implement it into our Python script, which basically determined whether there was obstacles on our path.
So the other related theory is our route calculation algorithm. So this is a big focus in our project, how the cars interact. So the main formula that we've been using is to calculate the estimated time of arrival for each car to an intersection point. So the things that we take into account are the intersection locations, which can be represented by those numbers on the grid, 1, 2, 3, and 4. The current location of the cars, as well as the speed of the car. For our software simulations that you're going to see moving forward in the presentation, we gave them both the same constant speed, just so that we can create scenarios where there would be a collision.
So for our hardware design, we have two main components, which is our self-driving car and our RC controller. So for our self-driving car, as I mentioned before, we have our ultrasonic sensors, our camera, and our RFID reader. This is all mounted to our Raspberry Pi. And then for the controller, we ran into a few issues getting the Arduino to control the RC car, the RC controller. So we ended up, our final solution for this was to have a simple transistor circuit. So this would allow us to have each direction be controlled by an individual pin on our Arduino. So the Arduino would just have to send a high or a low depending on what it received from our Python code. And at other methods we tried, we had like a servo and a potentiometer, but that ended up not working, so we went with the transistor. And then for health and safety, we have our obstacle detection by the camera and the ultrasonic sensors, and this is to avoid collisions into other vehicles and people on the road when we scale it up to a full-scale model. So just some pictures here. We have the circuit diagram of our self-driving car, which is on the left here. And then on the right, we have the self-driving car itself. So number 1 is our RFID reader, which is for the local positioning system. Number 2 is the ultrasonic sensor, which is used for object detection. Number 3 is our power supply, so we just use an external battery. 4 is our camera, and 5 is our Raspberry Pi.
So, like Tom mentioned earlier, we ended up integrating the Arduino controls through a simple transistor circuit, as you can see here. So basically, our leads from our Arduino are fed into this simple transistor circuit, which then simulates a button press for whichever direction we receive from our Python script that was fed serially to our Arduino. And here's a quick hardware demonstration. This is just us testing the keyboard controls for the RC car through the Arduino.
So for the software implementation that we had to think about several iterations that would help us create an optimal software simulation. So the first thing that we wanted to tackle was to create a one-car system. So this would be a system that would be on an 8x8 2D grid system, and each number would represent a certain object. So for example, the number 1 represents the starting point for the car. Number 2 represents the destination. 3 represents sidewalks or curbs. So these are pretty much boundaries for the system. The pathing was represented by the number 4. And 7 represents obstacles on the grid. Additionally, all the 0 points would eventually be represent RFID tags in our system. So every time that the car would go over a certain RFID tag, it would correlate to a position on our software grid. So these are all videos that we'll eventually show in our video demonstration. But so after we created a one-car system, our next step was to create a two-car system. So in our two-car system, we would take into account all of the routes that were created for the cars. And something that we're still working on is making sure that along with the other car route, that it also detects obstacles. So we were able to get it to work for a one-car system, and we're currently still working on creating it for a two-car system. Additionally, while creating these optimal routes for each of the cars, we're also minimizing the interaction between the two cars, which also increases the safety of the trip for all of the cars.
So for on the client side, when someone would go to use this, they would use the app that we created a very crude representation of. So the app would be able to be downloaded onto the car or pre-installed by the manufacturers, and you just input your destination and your route is calculated. So you can see the user enters the origin and then the destination. And then this is a representation of the car driving. And then you arrive at your destination. So that would be on the client side.
So we did unit testing for both hardware and software components throughout the year of progress. So on your left, you will see documentation for receiving RFID tags. So the RFID readers would detect an RFID token and send it to the database. So this was something that we were successful in doing. And on the right side, you will see a bunch of Python scripts, individual test scripts for each part of our, or for each component in our system. So we tested anything from sensors to anything with Arduinos and Raspberry Pis, etc. Other tests that we did, so we did integration testing. So a lot of our Python codes were strictly either for the hardware or the software in our project, and so we unified that into one source code so that we could integrate them together. And in terms of acceptance testing, we did a user acceptance test. So we asked other students to test our software simulation and saw how our simulation dealt with random inputs rather than us working on it. We also had several issues that we had to take corrective actions on. So a few of them are listed here: port forwarding errors, socket configurations for the Arduino, creating an image recognition classifier, and configuring the RC controller to interface with the Arduino. So in conclusion, the purpose of our automated traffic system is to optimize navigational routes for self-driving cars. In our functional decomposition, we had 5 main components, and we believe that those are components that could eventually be scaled up so that it can be effective for real-world application. Throughout our year, we also had to learn a lot of different things. So we had to really learn Python, the coding language, just because we mainly came from a background of Java and C++. We also had to find out how to create image recognition classifiers and to interface with the Arduino and the RC controllers, as well as some other things like socket, socket connections and stuff like that. So looking forward, if we decide to work on it, or if someone else would like to work on it, the things that would be planned for future work is to make this more scalable towards more than just 2 objects. So right now, the code only works for 2 cars, and it's very the code that we created is very flexible, but it would be better to sort of see the system work with 3 or 4 cars.
So here's just our demonstration video. So once again, this is just the testing of the hardware. This is all muted because it was kind of loud at some points. So yeah, this is just the testing of our hardware, and then this is the testing of our object detection classifier for cones, and then again for our stop sign. Yeah.
So this is our 1-car simulation. So we plotted the car in the top, and you'll see here that the initial optimal route would be just to go straight. So the destination is going to be south of it, but it realizes that there's an obstacle, and so it reroutes to go around the obstacle. And in our second system, which is our 2-car system, you'll see that both the cars try to plot their optimal routes, and well, you can see the grid there popping up in the terminal as well, showing that the destination as well as the starting points for the cars. And so you'll see these intersection points overlap, and you'll see them reroute so that they don't run into each other while running through the program.
So this is just us training our RC car to kind of drive forward and turn. Here it's demonstrating it's stopping. So you can see in the bottom that the terminal picked up the stop sign and was giving the signal for the car to stop. Here we're demonstrating the instructions being projected into our RC car. Side by side, you can see that the directions are in our terminal, and that car is actually responding to them.
Also, so we showed the last little clip there. What happened was we actually created a local system on wooden plates, but the problem was that our car's turn radius was too large, so we needed a larger area to actually test the car driving in the proper directions, and we didn't have access to a space that big.
So for our overall cost, it cost us about $297 for the whole project. But we would, if we were to sell this, we would sell the software behind the algorithm. So it would probably be a monthly subscription fee, because that's where software is heading, for $5. And then for codes and standards, we made sure to use all the codes and standards. So we did a lot of research into this, and we found that there were database standards that we had to use, like the Google API standard. And then we had for our communication between our devices, such as the Wi-Fi and the TCP. And then we had V2I standards, which is vehicle to infrastructure standards that we had to take into account. And then for autonomous vehicle standards, the safety standards, we had to take all of those into account when creating our autonomously driven car. And then our ethical issues that we considered. There's the 1968 Vienna Convention on Road Traffic, and this took into account driver-assisted vehicles. And at this conference, they stated that any driver-assisted vehicle needs to be able to be taken over by the driver at any point for safety reasons. So we made sure to take that into account. And then for other ethical issues, our project does not infringe on any copyright laws. We will acknowledge and give credit to any sources that we use during our project. And we will abide by all traffic and safety laws that are in the current traffic system. And these are our references. Any questions?
Yes, one question.
Okay. So very interesting work, first of all. I have a couple of questions. One question is, did you take into consideration the weather changes? For example, this camera is basically detecting the road based on the road roughness. For example, during snow season, when the road is full of snow, then the camera to be able to track this road while it's rough or has any of these conditions. Did you take this into consideration?
No, we didn't, but that is a very good suggestion that we should take into consideration.
And the second question is, you know, the eye contact is one of the major issues with self-driving vehicles, because it's still human to human contact when you drive a vehicle. It still has more accurate than the smart system. So, did you also take this into consideration? How smart is your system to adapt any point when you expect it?
So the end system ideally should have kind of classifiers that we could update through our database into our detection system that would be able to improve the accuracy of any objects that the car might come into contact with. The whole basis of the project is that the software that will be routing and detecting objects will be dynamic in that it'll react to any new obstacles in the course. So that's why when we had the simulation run with the obstacle, we also wanted to integrate kind of like another simulation where we could input the obstacle and see how the car reacts, but we ran out of time before we could get that in there. Any more questions? Thank you.